morning, everybody. Thank you all for coming. It's really great to see you here. Pierre, Tyler, and I are very, very happy to see you here, and we welcome you to our program. So now we can start with the first talk. Balint.
Good. Thank you very much. Thank you for inviting me here. Thank you for organizing this meeting. It's always an absolutely great pleasure to be in this place. And I'm very happy to see very old friends and new ones. So my talk will be, the title is a little bit scary, I think, so this H-1 reloaded, and indeed the talk will have a sort of analytic flavor, but it's about random walk in random environment. So I want to understand a particular type of random walk in random environment. Many of you, or some of you, were present about 1 year ago. About 1 year ago, I gave a talk with a very similar. Not the title was different, but the content was overlapping with this one in Bath. And I want to tell. Okay, first of all, that conference in Bath last year about random walks in random environment was very inspiring, and I started to rethink some parts of my old work, and this is sort of result of that thing. So thank you again for those people who organized that conference and those people who organized this one. So, and this is scary, so let me go to some examples first, because I decided to change the order to not to scare you so much. Namely, the following, don't read what's around there, just look at the examples, because this is a later page in my talk, but anyway, I give examples, then you know what to think about, what it is about. So these are maps of 3 cities. And these are streets and avenues in the streets, so these are very simplified something, so just northbound, east-westbound and south-northbound streets and avenues are there, and these are 3 different cities. And imagine that the mayor of or the council of the city want to make the streets one way as much as they can. One way to reduce traffic. And this one is fully grassroots, democratically decided, namely every single people living in every single block are asked whether they want the streets around them to be left clockwise or counterclockwise one way. And if there is agreement, then that street, as it is here, for example, then that street is made a one-way street. And if there is no agreement, then the street is not made one way, it's left both ways, right? And now you come with your car in this city, you start from the center of the city and drive, and the rules are that you don't go against the one-way traffic. You can go on these streets, and you can go only in that direction on the oriented streets. And whenever you arrive to a corner, for example, you arrive at this corner, you decide with probably 1/2 to go along a one-way street, which is allowed, and probably 1/4 to go on a two-way street, and probably 0 go against the traffic in a one-way street. Is it clear? So you have a random environment created first, and then you do a random drive, a random excursion with your car, which is a random walk. The question is how far you get, or where do you get in n steps, or in the time units. Do you get as far as an ordinary random walk? Do you get further away than an ordinary random walk, or closer? And so it's clear okay, we can make it a mathematical question. The other one, sorry, I made a mistake here. This is this city. Here, it was decided the one way, whether a street or an avenue is made one way, was decided for the streets themselves. And here I didn't tell you, I should have told that this is probably 1/2 is that way, 1/2 is. So the clockwise, counterclockwise, I didn't say that it's equally likely. Here, each single avenue and each single street is decided by a coin toss, whether it be one way in one direction or one way in the opposite direction. It's easier to speak about this because here at each single corner you have 2 out, 2 in. You drive your car. At each single corner you decide which one of the 2 possibilities to choose, and go like that. How far you get in n steps? Do you diffuse, or do you go further, or do you? Okay, I tell you, it's an elementary combinatorial fact that you will not get stuck. And it's easy to prove that actually it will be at least diffusive. But whether it's diffusive, by diffusive I mean scaled like ordinary random walk. Here is the most interesting one among these three examples. These are just examples. The 6-vertex model. Some of you know, some don't know. I tell you in 2 sentences what the 6-vertex model is. It's a random choice of orienting each single edge of the square lattice with the constraint that at each single site you have 2 in and 2 out. So the combinatorial restriction is that you have 2 in and 2 out at each single site. Otherwise, you choose randomly as you can. It's not straightforward that it makes sense, but it does make sense. It's a very, very interesting combinatorial statistical physical model. Now, I'm not able to. By definition of it, you have 2 in, 2 out at each single corner, at each single site, and the rules are the same of your driving, and again, the question is the same. So just to have something in mind. I have more examples in mind, but just I wanted you to have some concrete examples before I go to the formulas. Any guess about diffusivity or super diffusivity? I don't want to waste much time, but I ask those who don't know the answer, whether they have any intuition about what to expect.
Manhattan might be super diffusive.
Which one?
Manhattan should be probably super diffusive.
Yeah, and how are the other two? It's not straightforward. It's not straightforward. It is. You are right. Manhattan will be super. Okay, now let's go back to the first slide. Okay, now I will be a little bit formal. I have to be formal, sorry. I don't know what happened there. Oh, yeah, okay. Because it's my own computer. So we start with an ergodic, we start with a probability space. This is a space with a probability. I didn't write the sigma algebra, doesn't matter. And measure preserving maps indexed by ZD, which act ergodically. So this is an ergodic ZD action on a probability space. Right? Imagine you have random variables which are translation invariant, which have a translation invariant distribution and ergodic distribution. Right? So this will be my basic probability space. I will denote by this and just the nearest neighbor possible steps of my random walk, and I will denote by P a map from omega to 0 infinity to the end. So these will be the jump rates in the allowed steps. And the random walk in random environment, this is the most general definition of a continuous time random walk in random environment, is a continuous time. I stick to continuous time, and for good reason. A continuous time Markov chain on ZD, given the environment, given an omega, sample an omega, a random walk, nearest neighbor random walk, whose jump rates are given by this function shifted to the point, so with x shifted to the point. For the probabilities, this means that on each lattice site, these p random variables p are sitting, and they form an ergodic sequence. And when you are at site x, then those p's tell you the rate of the jump rates. And for some good reason, so this gives you everything, but I have reason to separate the symmetric part and the anti-symmetric part, symmetric and anti-symmetric part of the jump rates. Actually, it's good for me to speak about the square root of the symmetric part. That means symmetric part means add jump rate from here to there and there to here, and anti-symmetric take the difference, right? Of course, these are not new random variables, just are convenient to speak about. And for some reason, I will use the square root. So whenever you see r squared, that's the symmetric part of the jump rate. If b is 0, by the way, if you only have symmetric, that's what is called random walk among random conductances. So the difference of this story from the random walk in random conductances story is that I have anti-symmetric part, and that makes my problem non-self-adjoint and analytically more difficult. Good. I make some assumptions about the jump rates. The first assumption, and that's the structural assumption I make, the structural assumption that it's doubly bistochastic. So the jump rates pointing out from each single site sum up to the same value as the jump rates pointing inside. So see, these are, these are the jump rates pointing from, okay, if I shift to tau to x, these are the jump rates pointing from x to x plus k, and these are the jump rates pointing from x plus k to x, so jumping minus k. So this is double stochasticity, which is absolutely the same as saying that the anti-symmetric part of the jump rates add up to 0, which is a kind of divergence free. So these are some kind, the anti-symmetric parts are some kind of flow on the lattice, and they sum up to 0 means that they are divergence free. We'll see why it's important. So this is structural assumption, and integrability assumption is that the R's are L2. That means that are square integrable, right? That means that the symmetric part of the jump rates, the square of R, are in L1. And I also assume that the reciprocal of the R's are in L2. And for those who were there at my talk in Bath last year, this is a much weaker condition than assuming that the symmetric part of the jump rate is bounded below. That's what we call ellipticity. And my talk, essentially technical progress, what I report here is that I can relax conditions from ellipticity to this condition, which looks like a technical improvement, but it's conceptually important, and I will tell you why. The examples I showed you were all three were elliptic. The simple examples are elliptic. But I will show you other examples and important ones which are not elliptic. Good? Okay, so these are the assumptions I made. These are technical assumptions. And let's see the first consequences of the assumptions. First of all, the divergence freeness or the double stochasticity is actually equivalent to the following, and you see this is very important. You can look at the environment as seen from the position of the random walker. That's a classical object introduced in the 80s, early 80s by Varadan and others. So that's the good way of looking at it. One of the lecture talks maybe of Daniel Kius maybe, or maybe of Christophe Savot, in the title contains this concept of the environment seen by the random walker. So this is the environment seen by the random walker. Omega is the environment you see from the origin, and environment means the whole system of jump rates altogether. And when you move, you put the origin at various places, and this is a Markov chain. This itself is a Markov chain on the state space omega. And under this condition, this will be stationary and ergodic Markov chain, stationary and ergodic in time. So spatial ergodicity of the environment under the divergence-free condition is transferred to time-wise ergodicity of the environment process as a process in time. But I assumed no drift. That means maybe I didn't emphasize enough. Anyway, under my condition, there will be no overall drift of the random walker. So if you average out the randomness coming from the random walk steps and the environment, you get 0. So it's not the case that my random walker wanders away with positive velocity. And from the first two, of course, already I get for free by the ergodic theorem, I get a strong law of large numbers for the displacement of the random walker, right? And the other L2 condition assumed for the reciprocal of the jump rates will imply a diffusive lower bound. So what remains free, or after this first slide, these are simple things. Now what remains open is whether there is a diffusive upper bound as well. And that was my question related to the examples. And whether if there is a diffusive upper bound, whether a central limit theorem exists. And we'll see that two are not quite the same. And whether if, in other cases, is it true that you have a super diffusive lower bound? And some talks in this conference will be about this last question. Yeah. Now, for those of you who are more in stochastic analysis than discrete space, there is an equivalent diffusion problem. Namely, assume you have a random matrix, so an RD, a random matrix, So R omega X will be the random matrix at X, which is a D by D symmetric positive, strictly positive matrix, and a vector field, a random matrix field, and a random vector field, which is almost surely divergence field. The matrix field is positive definite. The vector field is divergence free, almost surely. And write down this infinitesimal generator for a diffusion. Assume things about these two objects similar or analogous to what I assumed for the jump rates, and you can easily transfer to the continuous space setup. And the question will be exactly the same questions about this diffusion in random environment. Right? Good. And a physical motivation, there are many this is a physically motivated problem. There are many dozens of papers from the last 30 years or 40 years about this problem, in particular about the diffusion problem, because it's physically well motivated. It's a kind of mathematical model for a particle suspended in a fluid, which turbulent fluid in a steady state, time-wise steady state, and follow a particle transported by the fluid. This is sort of a simplified model. Of course, nobody understands the turbulence properly well, but this is a kind of baby model for a still mathematically sufficiently difficult baby model of transport in turbulence. And there is a long history. Let me not waste time with the history now, but indeed there is a long history. The natural thing to do, and we always do this in random motion, random walk in random environment, or random diffusion in random environment. We always do this. We make a martingale. So this is the displacement of the random walker, and this is the most natural martingale decomposition. Namely, define the instantaneous drift if you are at a particular point, then in time dt, the expected displacement in time dt divided by dt, expected conditional on the environment, will be these two, actually the sum of these two functions, but I prefer to separate the anti-symmetric from the symmetric part, right? So the sum of these two is the instantaneous drift if the environment is omega, where you are, right? And what is written here is the most natural thing. So z is defined as x minus that integral, and it's clear that that's a martingale. And for the martingale, you know everything due to the martingale invariance principle and things. So you can apply things you learned about martingales. So this is well understood, but what is not understood is the integral of this function, whether this integral behaves, how these integrals behave. How these integrals behave, yes? And what comes first to mind to do is to do this martingale approximation. So there is a big theory, and by making this talk, I make advertising for this big theory. I call it Kipnis-Varadhan theory, which is a wonderful thing which came up in exactly 40 years ago in mathematical physics and probability theory. So, namely, I will speak about this in a very briefly in a general terms, namely that formulates some sort of theory about how to approximate these type of integrals when you have a Markov chain. Of course, don't think about a finite Markov chain, because in case of finite Markov chains, you have many ways to prove central limit theorems. This is about Markov processes in infinite dimension and complicated, difficult Markov processes with no gaps in the spectrum and so on, so where indeed the difficulty is there. Right? And by the way, maybe I was not explicit enough, my Markov chain is, sorry, I'm not able to learn this. The Markov chain eta sub s is the environment as seen from the position of the random walker. So everything is encoded there, because if you know this process, then you can decipher and you can get everything from there. Okay, I make more assumptions. I have to make more assumptions because in order to prove, okay, the problem was there, but in order to prove central limit theorem, the central limit theorem simply and diffusivity under those conditions will not hold each other. So I have to make more assumptions. And the assumption I make, the next one is this stream. Now, this is very, very formal, and I go back to some slides and I explain what it means. Don't think formally. I go back, it's easier to speak about this in the continuous space setting, and what in the continuous space setting, I have a divergence-free random, I have a random vector field on Rd. Think about R2 or R3, not higher for the moment. I have a random vector field, which is stationary, translation-wise, ergodic, and let's assume for the moment, say L2, square integrable. I assume only L1, but let's assume now L2 just to be able to explain that. So square integrable, stationary, divergence-free vector field. Now about divergence-free vector fields, if you learned some electromagnetics. Anyway, so the magnetic field is typically like that. So what people learn as physics students for sure is that if you have a divergence-free vector field, and there is in 3 dimensions, this is Helmholtz's theorem, I tell you now, 19th century mathematics. If you have a divergence-free vector field in R3, there is another vector field which in the physics community is called the vector potential, to which this original vector field is the curl. Now this is not always true, under conditions. Under conditions, not fast increase, so there are some technical conditions. Under conditions, if you have in 3 dimensions a divergence-free vector field, then there exists, so in principle, under good conditions, there exists another vector field to which this guy is the curl. In 2 dimensions, if you have a vector field in the plane, which is divergence-free and translation invariant, it's simple the case, then you have a scalar field, which usually in this community is called the height function, to which that vector field is the 2-dimensional curl. You have to understand what that is, right? Now, as this is the original field B was translation invariant, and it's the curl of another vector field, let me call it H, that will be of stationary increments, because it's derivative of stationary. In general, it will be of stationary increments. But in very lucky case, or in very exceptional case, it could be stationary. Right? Now, I go back to my slide, because I can conclude here. What this condition, the first condition, says is that we are in that particular case when the divergence-free vector field is curl of a translation invariant other vector field, vector potential, and not of a stationary increment vector potential. This is a restrictive thing. But so this is something structurally important. If I have this condition holding, indeed, so that means that this means in the lattice setting, this means the same thing, right? And I impose yet another integrability condition on this stream tensor. This is called the stream tensor in the PDE. If the stream tensor is also, so what you see there, stream tensor divided by the symmetric part of the jump race, this is technical. You have to do computations to find that exactly these are the conditions needed. If this is in L2, and this is what I call the H-1 condition, and I tell you in advance, for those of you who know some of H- of this Sobolev type of thing, that this is exactly the condition saying that the drift coming from the anti-symmetric part is in the H-1 space of the symmetric part of the operator, of the infinitesimal generator. Just for, anyway, it's an integrability condition. If this holds, so this will be my other condition, my next condition. And these are all my conditions, I assume. Namely, I assume that the stream, so this structural thing, I assume the integrability is as listed before. I have some bonuses coming in particular, for example, okay, anyway, I have some bonuses coming for free, and now I'm ready to go on to the examples. And you had time enough to think about the examples, to give me guesses now. So you know these examples, you know these, I will tell you the answer. For this one, the conditions hold. For these two, the H-1 condition does not hold. So you were right, but for neither of them. Actually, we sort of know what the order of super diffusivity is in these cases, and you will listen to Felix. He's not here yet, I think. You will see more about this. You will see more about something related. This is a discrete version. He will speak about a continuous version of this problem and the more amenable version of this problem. And that's it. Good. That's about the examples. I have one more example, but I don't know how. Okay, I will come. But these examples are elliptic, and Felix's example will be elliptic. And my issue is that I want to get rid of ellipticity. And I tell you on the next slide why. Why bother with non-ellipticity? Mathematics is beautiful, even if you assume elliptic, there are sufficiently difficult things there. Here is one motivation for looking at non-ellipticity. If you have an absolutely general random walking random environment, so think about my first slide without any assumptions about symmetries, whatever. Random walking random environment. For example, jump rates at every single lattice site are IID. No restriction, no algebraic type of restriction. Good. Then, in general, without assuming the divergence-free condition, the environment as seen by the random walker will not be stationary. And you can't do much because all this martingale approximation, everything work well when you have stationarity in time. You write down the equation you are looking for. I didn't do formulas here properly. You are looking for a measure, say mu, which is, or d mu, which is rho d pi. This was the a priori measure, which was translationally invariant. It's not stationary in time. It's not stationary for the time-wise for the environment as seen by the random walker, that process. You are looking for an absolutely continuous measure, which is for a measure which is stationary in time and absolutely continuous, actually equivalent measure-wise with the a priori measure. It's not clear whether one exists or not. Here is the equation. Everybody can write down the equation. Just sit down and write down the equation for this measure. You have to solve this equation in L1 for rho. I don't know whether this equation has a solution. This is a very, very hard problem. It's very easy to write down the equation, but it's hard. It's not, there is no, not. There are some very exceptional cases. For example, Christophe Sabot has a beautiful work on a very particular random walking random environment for which he can solve this problem in 3 dimensions, and I think he will report that he can solve it also in 2 dimensions. That will be his talk about. Essentially, anyway, we'll see that. Anyway, this is a hard problem. Nevertheless, if I assume that this is so, that Christophe solved this problem for me, then I can think about my original random walking random environment, a time-changed version of the original, namely take a new random walk in the same environment, but whose jump rates will be this one rather than the original ones. And this will be divergence-free. Of course, the equation is written like that. And now, asking about central limit theorem for the most general random walking random environment, if you are able to solve the stationary density problem, reduces to my original problem. I don't say that I can decide whether the assumptions hold or not, but that's a very explicit question. And look, there is Christophe Sabot's wonderful paper about solving this problem for Dirichlet random environments in 3 dimensions. Check my conditions for those functions which arise there. It's an analytic problem which might be very difficult, but nevertheless it's well formulated. So that was my original motivation. And in this case, nobody would assure that rho is elliptic. Rho will not be elliptic. So it's not the case that rho will take only values bigger than a positive lower bound. So even if you started with elliptic jump rates, when you solve this equation, you lose ellipticity. Right? So this is the motivation. Now here is a theorem. And this is new as compared to older. I'm sorry about this. I touch here something and something happens with my computer. Sorry. So the statement is the following. If I make these assumptions and note that this is the novelty, that ellipticity is replaced by the integrability of the reciprocal of the symmetric part of the jump rate, then the displacement is written as a main part and an error term. For the main part, I have a quenched invariance principle. This is a quench. That means that for almost all environments, under the measure condition to that environment, there is a convergence to Brownian motion with non-degenerate variance. And the error term converges to zero in probability, not quenched wise, but in probability with respect to the environment. So this is not an almost sure in the environment, but in probability in the, with respect to the distribution of the environment statement. Now, what's new here? Because this is I have this old paper. We have this old paper with Gadi Kozma published in 2017. So that's 7 years ago, when we had the very similar statement, exactly the same theorem, but with this ellipticity rather than that. Ellipticity condition rather than that. And the novelty is that it works without the ellipticity condition. And what is important is that in that proof, 7 years ago, more than 7 years ago, in that proof, Nash inequality played a very important role. So we could prove something, which I will show you now. We could prove something only by using Nash's inequality. But it's important, and those who are in this story know well, that Nash's inequality works under ellipticity conditions. There are some very sophisticated and very heavy analytical everything, in particular this paper by Morin and Otto, where this ellipticity is relaxed and dimension-dependent bounds are gotten in that way, but I'm not sure that is applicable, and maybe we discuss about this and we'll see, because that's done for random conductance story only, and possibly anyway. So there are other ways, but anyway, you would get in that way, you would get time-dependent, dimension-dependent and more restrictive integrability conditions. There are results like this, very strong results like this, and actually fully quenched results like this for the random conductance problem, not for the, as far as I understand. Now about the fully quenched, this is a little bit for the real expert, what is the difference between fully quenched and not fully quenched. Fully quenched means that you have the central limit theorem for almost all environments, for the typical environment, and the distribution conditioned on that environment. And my statement is that the convergence of the probabilities are convergence in probability with respect to the environment and not with respect to almost sure. It's a technical important difference. So there are results for the fully quenched. In particular, I have a paper related, okay, so it's the follow-up of that paper. This was in probability with respect to the environment, and this is fully quenched, assuming ellipticity, and the same thing slightly more, so the integrability condition here and there was not 2, but 2 plus epsilon, so I couldn't put it there, that epsilon, so that's why I wrote it there. But going back to this result, which I show you now, as a bonus, under these weaker conditions, I have existence and uniqueness of the harmonic coordinates, which is a very important component of the proof. There are 2 parts, existence of harmonic coordinates and control of some error term, but I do have existence of the existence and uniqueness of the harmonic coefficient. Good. And now, how much time? I don't know how much time.
We have plenty of time. Another
Plenty means how?
half an hour.
Come on. No, this. No, I don't. Good. I don't have things to speak for. Anyway, I will spend a couple of slides to it because I want to make advertisement to this wonderful, what I think very absolutely wonderful theory of Kipnis-Varadhan. I call it Kipnis-Varadhan. It started with this paper, his very famous paper in 1986 by Kipnis and Varadhan, but it's more than. This is abstract now. Forget about the concrete example or concrete problem I spoke about. It's about a Markov chain. A general, continuous time Markov chain on possibly infinite dimensional state space. Of course, I will have to make some assumptions about some operators, but it's very, very general what's coming here. Yeah? So assume we have a Markov chain on a Markov process, continuous time Markov process, which is stationary and ergodic on a probability space. And I call its infinitesimal generator L, I think, and resolvent lambda, and I think about them as acting in L on the LP spaces. I will probably need only P equal 2 or 1. But anyway. So it makes sense. And in L2, I assume that the infinitesimal generator can be decomposed as a symmetric self-adjoint and anti-self-adjoint part. This is a bit subtle because these are possibly unbounded operators, and then you have to say that this means that for the Knusser that these two operators have a common core on which they are essentially self-adjoint, respectively, essentially skew self-adjoint. Yeah? And I will also I define S is a positive operator. S is a positive operator, and in terms of the spectral theorem, you can speak about the square root of S, about S to the minus 1/2. This makes sense as self-adjoint operators. This is not elementary, but because they are possibly unbounded, but it's functional analysis. And I will define this space. This is what H-1 space. This is classical thing. The H-1 space will be take those functions in L2 for which this operator is a bounded operator. I mean, with the inverse. This is a bounded operator, so this thing makes sense. And due to elementary things, spectral theorem, as lambda goes to 0, this is an increasing sequence which may or may not have a finite limit. If it has a finite limit, that must be finite, and that's H-1. And by the way, it coincides with the norm of this operator applied to F. So I have this will be a dense subspace of L2, and close it with respect to this norm. That's the H-1. Okay. Keep in mind, we'll come back to this later. And what I want to understand is an efficient martingale approximation of this integral when phi is an element, say, from L2. I didn't write L2 anywhere. Anyway, is an element from L2. Not necessarily from H-1, from L2. I have a zero mean square integrable element, and I want to understand whether this integral converges or not. Whether the converges divided by square root of. I want to have a good martingale approximation, which will imply that I also have a central limit theorem. And here is the theorem. So this is what I call it the Kipnis-Varadhan theorem. What I quote here is my version from back in 1986, a paper in 1986, because the Kipnis-Varadhan theory was formulated for the self-adjoint case. And I needed non-self-adjoint in that particular paper back 40 years ago. And to my knowledge, this was the first time a non-self-adjoint version was formulated. Anyway, the proof is very much following the original Kipnis-Varadhan, but you don't have spectral theory, you have to use resolvents and so on. So here is the conditions. The conditions, but these look like abstract, and they are abstract conditions, so they are not so easy to check. Namely, that apply the resolvent to phi. If you apply the resolvent to phi, by abstract nonsense, it will be of order 1 over lambda. But I want to multiply it with square root of lambda, which is much bigger than lambda. and I want this go to 0. On the other hand, I want this s to the 1/2 operator, which was defined in terms of the spectral theorem. S is the symmetric part. R lambda phi to converge in L2. So if these two conditions hold, then I do have the good martingale approximation. Then I have a good martingale, then there is a martingale which is just what you want, such that the integral minus the martingale in L2 is small order of t. So that means that, for example, the central limit theorem for the martingale will transfer to a central limit theorem for the integral. Right? Yes, this is a very nice abstract theorem. You don't know whether it's worth anything because these are conditions which these operators you can't put your hands on them. No? So, okay, I have not so much time as Corina told me, so I will not spend so much. In the original Kipnis-Varadhan formulation, when it was self-adjoint, these conditions were all equivalent just with saying that phi is in h-1, and that's computed. And in all the applications, whether a function is in h-1 or not, in its own, it's computable, or easier to compute, or maybe not computable. And here are some abstract, so these are just simple identities. What you see here is the function phi you want to integrate, apply the resolvent to it, and take the scalar product. Now, for those of you who did any kind of this type of thing on Markov chains, even on finite Markov chains, you will recognize that this gives you the asymptotic variance of the central limit theorem you want to prove. So if you let lambda here to 0, that gives you essentially the asymptotic variance. This must be finite. That's the first thing you want, that the limit of this guy when lambda goes to 0 be finite. R lambda explodes as an operator. But this matrix element might stay finite. And that's what you want for, at least for finiteness of the asymptotic variance in the central limit theorem. This is an identity. This is simply an identity. You write down this thing, it's a simple transformation, it's an identity. And the fact that these and these separately, each of them is bounded by the h-1 norm of phi is an exercise. So this is a simple identity, and this is a not difficult exercise, right? So indeed, if we have phi in h-1, then at least we have an upper bound on the limiting variance. Not necessarily, it's still short of the central limit theorem, but at least the limiting variance is bounded, right? Now, another comment is that these conditions I showed you are very implicit. They are not checkable in general, right? Though exceptions exist, I said, because in that paper of mine back in exactly 40 years ago, I had a random walking random environment, non-reversible random walking random environment problem, which I wanted to prove, for which I wanted to prove central limit theorem, and I was able to explicitly check those conditions, but that's an exception. Usually it's not possible. Yeah? Now later, some years later, as you see, came these very, very famous papers about very concrete problems, which don't have time to mention now, but conditions were formulated for these things to hold. Not in these terms, but equivalent. And these are these papers of Varadhan and co-authors. And the most famous one is this graded sector condition, which I will not tell you now because it's so technical. I don't know what I know. It is so technical that doesn't make, okay, it's very important thing. But it's very, very technical, but the main problem is that the applicability is restricted to those cases when the L2 space is graded and the infinitesimal generator is adapted in a very good sense to that grading. For example, when the basic random variables you have are Gaussian, and then you have this Hermite type of grading of the Hilbert space, of the L2 space, and in some very particular structure is needed for that. We will see examples like that, I think, in Canizzaro's talk and in Otto's talk, as I don't know about that. But anyway, so it's restricted. It's very, very strong, but restricted in applicability, and generally it's not applicable. In particular, in my cases, it's not applicable. And here is a handy sufficient condition. I mean handy, I think it's handy. And I want to make advertisement to this one again. This is not a new thing. This was published about more than 10 years ago. And it's strong in the sense you will see that it's applicable. Namely, I want to make sense, I'm still in the very abstract case. I want to make mathematically properly sense of the operator you see here. S is the symmetric part of the infinitesimal generator. A is the anti-symmetric part or anti-self-adjoint part of the infinitesimal generator. And I want, sorry for this mistake, these two buttons, I confuse them all the time. I want to make sense of this operator, so apply inverse of square root of S, A, and inverse. This is a very dangerous thing because none of these operators is bounded. So it's not clear whether this can be at all defined that you take a function f, it must be in the domain of S minus 1/2, you must land in the domain of A, apply A, you must land in the domain of S to the minus 1/2 again. So this is so I define abstractly a subspace of A, which is H minus 1, so S in a subspace of H minus 1, so S minus 1/2 makes sense. Applying S minus 1/2, you land in the domain of A. Applying what follows, yes, A, you land again in H minus 1. If you have something like that, then at least for those functions, this makes sense. I didn't tell you why I need this operator, but I will show you in a moment why I need this operator. It may be the case that this B, this subspace B, is absolutely thin. It may be the case that it contains only the zero element of the function space. It's so abstract. We'll see it's not the case. But even if it's dense, which we need in L2, if it's dense in L2, then this operator is anti-symmetric. That's straightforward. But it's not, of course, to those of you who learn functional analysis and unbounded operators, you know that this is not sufficient. You have to close it, and the closure must coincide with the adjoint, with the negative of the adjoint. So there are cases when it doesn't happen. So this should be checked. It may happen that the closure of this skew-symmetric operator is not the same as the adjoint, as the negative of the adjoint. And what we prove in this theorem is that if it happens that this operator is densely defined and is essentially skew self-adjoint, that means its closure is equal to its negative adjoint, then we are home. Then those conditions hold. So it's a very abstract thing. It looks like an abstract thing. You have to understand this operator. Let's see why it helps. I'm sorry, I told that there will be some functional analytic, but this is the last abstract slide, and you will see how it applies. You will see how it applies. Okay, first let lambda be positive. If lambda is positive, then this operator is well defined, and it's a skew self-adjoint operator indeed. As long as lambda is positive, there is no problem in defining this operator as a skew self-adjoint operator, and if it is a skew self-adjoint operator, then identity plus that is invertible, and its inverse is bounded by norm 1. Elementary, right? And this is elementary computation, so we are with lambda still positive. As long as lambda is positive, you can write down the resolvent in this form. This is elementary manipulation, algebraic manipulation, nothing more. So this is true up to there. K lambda, this operator K lambda is uniformly in lambda down to 0, uniformly bounded by 1 in norm. And what I claim, that if by some miracle it happens that it's not only bounded by in the strong operator topology, it converges to an operator, then the conditions hold. And that's a elementary, let me not go through it, it's just strong convergence, spectral theorem applied. It's a straightforward thing. So what is needed, is that this sequence of operators, which is well defined as long as lambda is positive, and is bounded as uniformly in lambda, converge in the strong operator topology when lambda goes to 0. And what the theorem says, but the rest, which is not written down here, is that indeed under the conditions which I told you, namely that this B exists and this is okay, this strong convergence holds, and that's an argument which is reminiscent, for me at least, it looks like a Trotter-Kurtz type argument. I'm not going to tell you now. Good. Let's go back to our main issue, to my main problem. So I'm back to my main problem. So the Hilbert space. Okay, the LP omega. Now I'm back indeed in my case. Omega are scalar functions over the probability space, which are LP, zero mean. I call by V sub P what I call vector fields on the left. Vector fields, I call them vector fields, which will be n component. So remember, n was the 2D neighbors. So in each direction and being in this space means that UK is in that, so each component is in that space, and there is this kind of symmetry that pointing the value of pointing that way and the value pointing backwards are negative to each other, right? So this condition, so take all functions with n components for which this condition holds, and those will be in my VP space. And the UP, I'm sorry, I have to introduce some spaces, otherwise I can't do computations. About these functions, I think as about vector spaces, so when lifted to ZD by shifts, they form a flow, a vector space on ZD, right? And UP is a subspace of VP, those flows which are rotation free. So, okay. So I have the lattice. I have these functions of omega, but you may think about them as fields on the lattice by shifts, right? So the first condition, the VP condition, means that when you raise this to the lattice by defining u at x being u translated to x, that means that value plus that value are 0. So these are opposite of one another. And the second condition for UP means that if you add up these, they add up to 0. So they are rotation free, right? So these are my vector spaces, but I have one more needed here, namely that's mapped from the rotation-free vector spaces by a multiplication. So it's the image, essentially, of course you have to be a bit careful about closures and all that, apply the inverse, so multiply these by the RK functions, and that's what you get in this space. I'm sorry, I need these because these will be the proper objects we need. And we need also some operators. Okay, I know my time is running out, so I have some kind of gradient and divergence. Namely, what does the gradient do? Take a function, shift it, and subtract the function itself, the most natural thing, which lifts a scalar field to a vector field. The divergence does the following: take the values along the outpointing edges and add them up. But this is the same due to the conditions of definition of that space. This is the same as what you expect from a divergence, namely that add up the differences. I mean, these discrete derivatives in the various directions. These are very elementary. These are defined in terms of shifts, so very simple operators. I have also some multiplication operators, namely, take a vector. The capital R means the case component. This is an error here. This is small r. The case component of R applied to K is defined by RK, small rk, multiplied by UK. And I have this H, which is very bit complicated, but it's again essentially a multiplication operator and maps vectors into vectors. It's like multiplying with these stream tensor field. And here it's important that the stream tensor field was traced translation invariant, otherwise I couldn't define an operator like this, right? And using these operators, the symmetric and anti-symmetric part of the infinitesimal generator are written like these. And you see what happens here, which is very funny actually, and it happens in many cases when, in partial differential equations in particular, they call divergence form operators and so on. So the anti-symmetric operator is written this way. There is some structure here which helps. And here are some key facts, and then I will finish. This is probably my not quite last slide, but almost last slide. First of all, and this is valid under the assumed condition. So far, I spoke about abstract things, and this is particularly true only under these conditions. Namely, that H-1 is in L1, is a subspace of L1. This is not always the case. In this particular case, H-1 will be in L1 under my integrability conditions. And I have a very nice explicit formula or variational formula. There is always a variational formula for H-1 norm. But what I mean is that it's explicit here, so it's computable. And another important thing is that the L2 space and the K2 space, recall what the K2 was a subspace of the vector space, of the subspace of the space of vector valued functions, right? Are isometric. There is a natural isometry from the L2 to the K2. This is due to this structure. This is due to this structure. There is a natural isometric identification between the L2 space and that I guess you didn't quite grasp what it was, because I wouldn't have been able to do it in that short time. But anyway, between another space. But in this space is easy to compute, easier than the. So what I want to say that this operator S-1/2 is not computable. That's something which you don't see. You can compute with it. But due to this isometric lifting, you will see on the next page, proving skew self-adjointness of the antisymmetric part will reduce to proving skew self-adjointness of an essentially a multiplication operator on a Hilbert space, which is an easier thing. And here is a remark for those who know what Riesz kernels are, so that these are somehow reminiscent of what are called Riesz kernels in harmonic analysis. And here is the proof then. First of all, due to the first, so 1 and 2 correspond to 1 and 2 on this slide, 1 and 2 on this slide. Due to the first formula, checking H-1 is a computation, a nice computation otherwise, but a computation. And proving the skew self-adjointness, let me not go through it again, but means that due to this isometric lifting, is proving skew self-adjointness of this operator. I mean, more or less like this operator, there is some projection there. But what the main thing is that this is essentially a multiplication operator, and proving self-adjointness, skew self-adjointness for multiplication operators is routine. And I didn't have to use Nash's inequality. This part of the old proof was a more convolved thing through Nash's inequality, and that's not needed, that's the message. And I think I'm almost done. I have some comments about the harmonic coordinates here, but this is for the expert. Maybe I'm happy to discuss later about other details and other examples. I wanted to tell you another example, but I don't have time left. Thank you very much.
Questions?
The proposition, is it what you mean when you say that you solve the harmonic coordinates?
Yes, yes. So that this equation has a solution, that WK will be a solution, that will be actually a gradient, and you construct the harmonic coordinates from that gradient.
But of course it's not explicit.
It's not explicit, but you don't expect. Okay, sure. This will never give you explicit formulas, of course, but it gives existence and uniqueness within a class.
So I know, it's clear that the H-1 condition is optimal in the case even of uniform diffusion. Did you say something about the optimality, about the L2 assumption?
Now, this is what I don't know. Sorry, L2 maybe first of all, but I don't know whether indeed there are, okay, you will understand what I'm saying, for sure. There are two conditions. The skew self-adjointness of that operator and the function you integrate be in H-1. And both, and actually in this particular case, the one implies the other one. So if I know H-1 for this particular function which comes as the flux for the displacement, then I also know skew self-adjointness, but not the other way. So let me make a dichotomy. Maybe this is your question. I'm not sure whether this is your question. There are four cases. So this is B equals B minus B star. This is phi in H minus 1, right? Yes, yes, no. Yes, no. Now if this happens, let me see, let me not make mistakes. If phi is in H minus 1, then this is like excluded, right? In this case, I have the CLT. If in this case, what happens in this case is that, I don't know, you have a diffusive upper bound, but you may have no central limit theorem. So it's a question. So in this case, you have upper bound, diffusive upper bound, but CLT, I don't have any counterexample. I'm trying to find a good counterexample when indeed, this is very interesting that you have, physicists would say that, okay, once you have a diffusive upper bound, it's like the Gaussian. No. And this is the case you know well. This is the case when super diffusive. Right? And super diffusivity holds. This is not a theorem that you always have super. In particular, all cases we know, in these cases we have super diffusivity. Did I answer? Did I catch your?
It's a good answer. It's not.
It's a good answer to another question. It's a good, then tell me what was. tell me what was it.
I mean, it's at some point, but I don't want to monopolize this one. So at some point you had this. You started out with kind of an L2 bound on the inverse ellipticity.
Yes.
And so my question was more practical. How, is it clear that if you relax that and say it's 1.9, then it's wrong, or is it?
I can prove diffusive lower bound. Let me see how when it comes in. I need that in many cases because in many, for example, I can't recall now exactly everything, but I have to. But for example, that H-1 is in L1, and these type of things rely on these bounds. I'm not sure I can tell you now exactly where which is used, but I think it's quite important.
And that question with respect to the picture which you drew, how is that? Where is that hidden?
How?
I ask you later.
Okay.
Other questions?
Yeah, thanks for that. So physicists here, so the Helmholtz theorem, I got them. So just on this picture, when you have u equals u minus k, what happens if you have asymmetric rates? What happens if u divided by u minus is not 1? In a sense, so basically, if you have, so I'm thinking about time reversibility.
This is not reversible.
Yes. Okay, so this is not time reversible.
This is not time reversible. The time reversible, I mean, at least what we, in probability theory, what we call the reversible case, when that corresponds to the fact that would be the fact when my B, so when the anti-symmetric part is simply zero.
It's gone.
It's gone. Only the conductance is up. That would be the reversible in the Kolmogorov time reversible.
And any other questions? Okay, if not, let's thank Balint.
Thank you.